Okay, let's look at the next problem here. The largest rectangle in histogram. This is also sometimes known as the maximal rectangle under Skyline problem. So you're given in this problem an array of numbers again, where the numbers stand for the heights of buildings. Right? You might remember from last time the first problem we did, buildings with an ocean view. So kind of like that. But here, instead of looking for the buildings that have an ocean view, we are looking for a rectangle within this skyline that has the maximum area. So in this toy example here, where the heights are 215, 623, by visual inspection, you can see that this rectangle probably will have the highest area. So it's going to have a width of 2 and a height of 5. So the area would be 10. Right. The other large rectangle we could try to make would be this one, but it could have a height of 1, and with a width of 5, it would still have a smaller area than 10. So we are supposed to return 10. In the second example here with just 2 buildings, the rectangle with the largest area could be either this 2 times 2, which could be this 4, or even this rectangle by itself with a height of 4 would be a valid optimal rectangle. If this height had been bigger than 4, then it would have to be just this single building by itself, which would have the maximum area. So all the heights are non-negative. And so we need to find the rectangle with the maximum area. So let's start from the basics again. Let's try a basic decrease and conquer strategy where so it doesn't look like order matters in this problem. You can go in a left to right order. Since there is no such thing like an ocean on one side. So let's say I know the answer. I know the answer to the problem for the first n-1 numbers. And as a lazy route manager, I'm asking the question, in what way can the last number contribute to the answer? So the last number could contribute to the answer by having at least part of the optimal rectangle intersect with it. Right? Maybe part of the optimal rectangle could lie under or inside my building, inside the last number. So if we ask how can the last number or the rightmost number contribute to the globally optimal answer, by having the optimal rectangle end at my index, end at the rightmost index. Wherever it starts. So if you look here, as we are scanning this array from left to right, well, here the rightmost number is 3, and we don't have a rectangle that the optimal rectangle doesn't touch 3. But if we ask the question, what's the best rectangle, what's the optimal rectangle we can make that includes this 3? Right? And if everyone had that, if every manager had calculated that answer, then we could take the best among them. So the local problem that I want to solve is, what is the optimal rectangle what is the optimal rectangle which includes my number? Okay, so so if I am the rightmost number here, I would say I know that my height, let's say my height is some h. So this is what I'm looking at. I don't know what lies on my left, but what's the optimal rectangle which includes my number? Well, if the building to my left is of height h or more, then the optimal rectangle which includes my number could extend further to the left. If the building to its left is, let's say, even taller than it, then the optimal rectangle which ends at my number could extend even further to the left. In fact, I can keep including the numbers on the left until I reach a point where maybe the height is this. This is also included. But then suddenly I have a building that's shorter than h. And that is a place where I cannot have an optimal rectangle, my optimal rectangle continue further. Right, so the optimal rectangle which includes my height would have to be this one. So I keep looking left until I see a number which is my previous, that means on my left side, smaller, previous smaller number, until I see a number that is smaller than my height. Okay, so that's what I'm thinking for the rightmost number. For the rightmost number, if I have the value of the previous smaller number, up to that point, right? This, if you recall, this is what we called last time. There was actually a problem called the online stock span problem. This is what we called as the span of my index or my number, right? I look to my left and I look at all, I continue until I see values that are equal to or greater than me. And then as soon as it stops, as soon as it plummets below my value, I stop there. I don't include that, but I include my own index. And that's what we defined, or that's what one of the lead code problems itself, the online stock span problem, I defined as the span, which we saw came in handy in some other problems also last time. So it'll come in handy today as well. So this so far is looking good because I can at least I can at least imagine that if I had a monotonic stack that would help me that each manager was building up in an amortized way, each of us could calculate the span of our number on the left side and use it to find the optimal or the rectangle with the maximum area, which includes my number. Let's see if this generalizes to an arbitrary index. So this is what I did for the rightmost number. Right, this number at index n-1. Now let's think about a general index I. So if I'm doing this, I'm actually depending on my subordinate to have already filled in the monotonic stack here. So my subordinate would have done the same thing. And so we would have in an arbitrary point in the hierarchy, a manager who is trying to find the answer for this blue rectangle, this blue prefix of the array, and trying to ask the question, what is the optimal rectangle which includes that manager's number? Now, since this index I is in the middle, what we would end up calculating if we were to generalize this procedure is the maximum rectangle, the rectangle with the maximum area, which ends at, which starts anywhere and ends anywhere, but the ending index is entirely covered, or the height of the last building, the rightmost building, is entirely covered by the rectangle. Right? That's what we are going to get if we were to generalize what we have written here so far. But the fact is that even though these examples, both of these examples actually that LeetCode has given are rectangles of that type, if you look at the rightmost index, well, actually this one isn't. This one isn't. The rightmost index here is not completely covered by the optimal rectangle. Right? And so that's why it's possible that my rightmost, when I'm looking for the optimal rectangle which includes my number, it's possible that my number might not be entirely included. Maybe it could be partly included. Now that's a problem, because if it can be partly included, then I don't know to what extent it's included. Is it included up to this height, this height? There are, whatever the value in my index is, I have that many number of options for how much that optimal rectangle could include. So if I were to try to find the answers for all of those possibilities, that would be too much, because the values of these numbers can go, arbitrarily big. So ideally, I wanted the rectangle to cover my entire height, but it doesn't. Okay, so this is where I'm kind of stuck at this point in trying to use this approach. But one thing I notice is that even if the optimal rectangle doesn't include my height entirely, it has to include some height entirely. Right? It's not possible for the optimal rectangle to look something like this. Right? I'm just going to draw a very rough skyline, almost like a curve. Okay, but imagine that these are all discrete, discrete buildings like this. Is it possible that the optimal rectangle could look like this? Well, no, because this rectangle, this blue rectangle, doesn't cover any of the heights to the maximum height. right? It just covers each of the buildings that it spans. It doesn't touch the roof of any building. And because it doesn't touch the roof of any building, we could extend the rectangle by one more floor to increase its area. So the maximal rectangle under the skyline does not have to cover the entire, it doesn't have to touch the roof of the rightmost building, but it does need to touch the roof of some building. So that's an observation here. So the maximum rectangle need not. So the problem that I've run into is that the maximal rectangle need not touch the roof of the rightmost index. But it does need to touch the roof of some index which could be internal to it. Otherwise there would be a contradiction. Otherwise it wouldn't be maximal. Now this index is internal. In general, it's going to be internal to the rectangle. Right, so it could look something like this. Let's say this is the index which is covered entirely by the rectangle up to the roof. So maybe this is the maximal rectangle which touches it up to the roof. So other buildings have to have at least that much height. Maybe this one has a height a little more, maybe this one is equal, maybe this one is even more. This one is like this. So this is the index we are looking at. And there can be multiple such indices. So let's say I am a manager who's taking the responsibility, whether we look at do a left to right scan or a right to left scan. I am focused on the leftmost or the rightmost index of my subproblem, which in general is going to be an index I. So the question that I want to ask is, what is the maximal rectangle that touches the roof of my index? Right? And the change that I'm making from the earlier approach here is my index had to be also be the rightmost index of that rectangle. It should cover my building entirely. It should touch the roof of my building, but it had to strictly end there, right, from the left. Now I know that it doesn't have to end there. So the slightly different question that I'm asking now is, what is the maximal, the local problem that I'm trying to solve is, what is the maximal rectangle that touches the roof of my building and it could extend on either side. right? It doesn't have to end there from the left. It could extend on both sides of it. Now you might think this is a problem because, you know, if you're doing a left to right scan, we're assuming there is nothing on our right side, but now we are allowing for the maximal rectangle to also extend on the right side, and there's no way getting around that, because if you're not aware of what's on our right side, the answer that we get is not going to be the answer to this problem. So in some sense, we have to be aware of what's lying on both sides here of our index. So in other words, we have to be aware of not just how far I can extend the rectangle on my left, right? I can extend it all the way here up to this point. Maybe I can't extend it beyond this point because the height after that is smaller. I also have to be aware of how much I can extend it on my right side. And maybe I can't extend it beyond this point because, again, either there is nothing beyond that, or the building that lies beyond that is smaller in height. So I would say this is the previous smaller building, previous smaller height. This height is actually the next smaller height. So the maximal rectangle that can include my number is going to extend on the left up to the previous smaller height, and is going to extend on the right up to the next smaller height. So if I knew for myself what's the previous smaller height and what's the next smaller height, I had that data available readily, I could instantly compute the area of the maximal rectangle which touches the roof of my building. Now the question is, how can I get that? How can I get the previous smaller height? If I was doing a left to right scan, there's no issue in getting this, because each manager in the chain could be accumulating that monotonic stack. And so when it reaches me, I would know what the previous smaller height is. That would actually be, you can say, the left span. So everything up to this, I'm going to call as the left span. Right? It's the span on the left. But the problem is, in a left to right scan, I would not know what the next smaller height is. To get the next smaller height, I have to do a right to left scan. So it looks like this would have to be done a priori for me to be able to utilize it, right? If for all of these buildings, we need the next smaller height to already have been pre-computed. And that's not a problem. We could pre-compute it in a right to left linear scan as part of the initialization, and maybe just use it. So the next smaller height is going to give me the right span, the span on the right side. Oops. So I hope you see where we are getting here. For each number, we actually need both the left and the right span. If we have this data pre-computed, it doesn't matter whether we do a left to right scan or a right to left scan, each manager can instantly compute the maximal rectangle that covers their building up to the roof. And that would be their local contribution to the global answer. And we just take the max of all the local answers. That would be our global answer. Any questions about the algorithm. So the plan is pre-compute the next smaller height, or we can say pre-compute the previous smaller height. Let's say we pre-compute both of them, and then we, utilize that data in doing a left to right or right to left scan, whatever it is we are doing when we are looking at index I. So previous smaller heights can be computed for all the values in linear time. Next smaller heights can be computed for all the values in linear time. And having pre-computed them, it would take a constant amount of time to find the area of the maximal rectangle, which covers my building up to the roof at index I or any I. So that means the local answers can also be pre-computed, can also be computed then in linear time. And so the whole thing can be done in linear time. But we would need two different monotonic stacks. So what makes this problem complicated is both of these are required. It's not sufficient to just have one of them. So far in the monotonic stack problems, our focus was exclusively on calculating for each number, what's the previous smaller or bigger number or the next smaller or bigger number. Here we need two of them to be available to us. And that's what makes this a hard problem. Okay, Safiq.
Hi. Yeah, actually, we moved ahead basically. Initially, I was thinking like here we are going to apply the approach of divide and conquer or something, but it seems like we still are focused on stack.
So, yeah, I know that this problem has been solved using divide and conquer, or at least that's what they say. But given how infrequent divide and conquer is helpful, how infrequently it's helpful, I hesitate to start out with a solution like let's use divide and conquer, because it would just show that I already know what the solution is, because we never start out with divide and conquer for almost any problem, unless we end up at a dead end for try every possible decrease and way to undo the bottleneck and decrease and conquer, and we fail. So that's why at least I wouldn't. There is no way I can recommend divide and conquer here, because if I did, the next question you're going to ask is, well, how do I know I have to use divide and conquer for this problem but not for other problems? See the problem there, right? If I give you if I say that let's use a divide and conquer strategy, you cannot just start applying it for this problem and not for any other unseen problem. How do you know that for a new unseen problem you shouldn't use that strategy? So we need an approach that would work for a new problem as well, which you don't know the solution for.
Agree.
Right. So that's why I'm not looking at it that way.
Okay.
Right. So you can think of it like a divide and conquer algorithm. You can take the same algorithm that we've come up with and look at it as a divide and conquer algorithm also, but it's it wouldn't be helpful in an interview, according to me, because in an interview you need to start out with one trail, right? You don't know where that trail is going to lead to. Maybe it leads to dynamic programming, maybe it leads to sliding windows, maybe it leads to prefix sums, maybe it leads to monotonic stacks. But the starting trail has to be one. And if the starting trails themselves are like 5 or 6, then it becomes very hard to pick which one to start with. So my starting trail is always decrease and conquer. Okay, so no other questions, right? You can write the code for this.
Yeah.
So what I'm going to do is pre-compute the previous smaller height and next smaller height for every number in the array, and then use it in a left to right or right to left scan to find the local answers, maximal rectangle covering that number, and the global answer would be the max of all the local answers. So you can say pre-compute the left and right spans. So let's say we are doing the left span first. Okay, now one of these could be done with the final left to right scan as well, but just to keep it conceptually clean, I'm going to pre-compute both of them rather than merge one of them with the actual scan. So how do we compute the left scan? Well, we just use the template for this. We want the previous smaller values for each value. So we will use our template. Right, let's find the previous smaller values. How do we do that? We have to start from the left. We have to do a left to right scan here. So for I, varying from 0 to n minus 1. Right, n here is the size of the heights array that's given. So using the template, while the stack is not empty and the element at the top of the stack is not my previous smaller value because it happens to be greater than or equal to my value, and the element at the top of the stack happens to be greater than or equal to my value. Sorry, not heights here. Would keep popping the stack. And finally, when I'm out of the while loop, I might have to process the answer. So if I see what the next, what the previous smaller value is, I want to compute the left span actually, because the area of the rectangle that I'm going to need for my local answer is going to have a height that is equal to the height of my building, but the width of that rectangle is going to come from the width of the or the values of the left and right spans. So I need to find these left and right spans. How do I get that? I need to know the index of my previous smaller value. Then only I can compute the left span, which is what we did last week. So what we will need to insert in the stack is not just a bunch of heights. We will also need to have the indices available with those heights. So what we actually insert in the stack here is a value comma index pair, just like we did in some of the problems last time. So I'm going to look at the value part on the top of the stack. It's going to be an ordered pair, value comma index. Right, so let me say the stack stores value comma index So I look at the value. As long as the value at the top of the stack is greater than or equal to my height, I keep popping it. And once I get to a place where either the stack is empty or I see my previous smaller value on the top of the stack, I can compute my left span. So if the stack is not empty, right? So that means I'm looking at my previous smaller value here. Whatever this index is, right? Whatever this green index is, the left span is going to be everything beyond it up to index I, including index I. So whatever this green index is, if I do I minus green, that will tell me how many steps I have to take to walk forward to reach I, and that would be exactly the left span. So I minus the index of this, I minus the green index or the index of that previous smaller value. So my left span for my building, my local left span, right? So let's assume that left span values are going to be stored in a array size n, initialized some default values. They will all get overwritten anyway. Let's say 0. So left span of I is going to be I minus the green index, or the index of the element at the top of the stack. So whatever the element is at the top of the stack, if I look at the second value in that ordered pair, that's going to be its index. We did this last time. Else, if the stack is empty, that means there is no building further to the left, then everything up to index I from the extreme left is the left span. So left span of I in that case would be all the indices from index 0 to index I. So that would be I plus 1. And having done this, this was the processing part. We need to make sure we insert our value. st.push. We insert our element into the monotonic stack. What we are inserting is a pair. So we will insert the value, heights of I, with the index as a pair. And now at the end here, all the left span values for every index are sitting in the left span array. We do the same thing for the right span. Let's write parallel code for that. You just have to look at each line here and just write a symmetric code for computing the right span. So the right span array is going to be a one-dimensional array of size n, where n is the length of the heights array, initialized to 0. So let's start out with an empty monotonic stack. You want to find the next smaller values. Find the next smaller values to get the right span. For each element. Since we are looking at the next smaller values, we have to do a right to left scan. So in the range from n minus 1 down through 0. While the stack is not empty, and the element at the top of the stack, in particular its value, is greater than or equal to my value, right? We are in both directions, we are trying to find the next smaller value. So as long as the values I see on the top of the stack are greater than my value, I know that value cannot be my next smaller value. So I'm going to clobber it. Then we come to the processing part. If the stack is not empty, that means my next smaller value is lying at the top of the stack. So I can set my right span based on whatever the index of that next smaller value is. So here, going back here, let's say this is the value I see at the top of the stack. So the green index this time is bigger than I. But again, the definition of right span is that it includes everything from index I up to, but not including the green index. So the number of size or the length of the span would be the difference between the green index and I. So instead of I minus green, we go to green minus I. So instead of I minus the index at the top of the stack, we do the index at the top of the stack minus I. Otherwise, the right span would extend all the way from index I up to index n minus 1, since there would be potentially nothing on the right side. The stack's empty. So if I have, how many values are there from index I to index n minus 1? Well, n minus 1 minus I plus 1. That's n minus I. Right? The size of this subarray is going to be the end index minus the start index plus 1, because we have to include both endpoints. So n minus I, or you can say the length of heights, that's n minus I. So that's the processing part. How do we process the next smaller value? We look at the index and compute the right span based on that. And finally, according to the template, we have to push or insert our current element on the stack. And that's going to get inserted as a pair, the value along with the index. So if we compare this to the code here, we have pre-computed the left spans, we have pre-computed the right spans as well. And now we are ready to find the local answers for each of the managers. So we could do either a left to right scan or a right to left scan. It doesn't matter. I'm just going to do a left to right scan. Okay, we're going to use the left and right spans to compute the local answer. So what's the local answer? Compute local answer for index I. The manager who's looking exclusively at the building at index I. So the height of the maximal rectangle that touches the roof of index I is going to be heights of I, the value at that index. What's the width of that rectangle going to be? It's going to be left span plus right span. But when we add both of them, we are including index I 2 times. So we are double counting that index. So we need to subtract a 1 from it. Left span plus right span minus 1 would be the width of this rectangle. So we can say the local answer is going to be height of the rectangle multiplied by the width of the rectangle, which is left span I plus right span I minus 1. Having computed the local answer, we will, this is an optimization problem, so we will update the global answer if it beats the current global answer. So let's call it global max. Just to make it clear, we are maximizing the smallest possible value for a maximal rectangle. For the area of a maximal rectangle is 0. So that's why I'm initializing global max with 0. And then update global max if the local max value is bigger than it. The local answer is bigger than it. And return the global answer at the end. So that's our code. Pre-computing the left and right spans takes linear time. This final scan also takes linear time. So the time complexity is linear. Auxiliary space. There are actually two monotonic stacks we've used because we had to find both the previous and the next smaller values. But the asymptotic auxiliary space used is still order n. Whether it's one stack or two stacks, doesn't matter. We also used a couple of local span and left span and right span arrays to store the values, and so they also use additional auxiliary space, but that's also order n. So the combined auxiliary space used is order n. Okay, questions about this, Garrett?
Can you go through again? How did you define the right versus left? Like, why is it you take length of height minus I and then I plus 1 for the left one?
Oh, so the left span. So the left span is essentially how many indices to the left are there which are greater than or equal to my index, right? Before the stock value falls, if you remember, or before it rises, it was something like that in the online stock span definition.
Okay.
So if I know what the index is here, where I see a value which is smaller than my value for the first time. So let's call this index as green. So the number of steps I need to walk forward, starting from the number green and ending at number I, is I minus green, right? That's what it means to do subtraction. How many, if I'm on a number A at the number line, how many steps do I need to walk forward to reach number B? Would be B minus A.
So that's what I understand. I don't understand the else clause. Why do you put I plus 1 for the left span and you put length of array minus I for the right span? Because I thought by symmetry you put I minus, well, I guess I don't understand I plus 1, and I don't understand if you put I plus 1 for left, why don't you put I minus 1 for right?
So if it turns out that all values on the left are bigger than my or greater than or equal to my value, I'll end up clobbering all of them. The stack won't have anything left. If the stack doesn't have anything left, that means everything on my left is greater than or equal to my value. So there is no index on the left side. Or another way to say it is the index on the left side is -1. Right? I mean, this is not a valid index. This would actually become something like -1. There is nothing here. So I could use the same formula and I could say, you know, I minus that index, which would be I minus -1, which would be I plus 1. Or another way to put it is all the indices from 0 to I make up my left span. So how many numbers are there from 0 to I plus 1.
Okay.
So that's where I get the I plus 1 from.
I see.
This part is
Okay.
clear?
Yeah, this part is clear.
Now for the right span, we do the same thing. If we go back to this diagram, if the stack's not empty, then this green index is the first place where I see a smaller value. And so how many values are there from I up to green minus 1? Right, that would be green minus 1 minus I plus 1, or green minus I. Does that make
Okay.
sense? So that's where I get that from, if the stack is not empty. Sorry, this one. And if the stack is empty, then all the values on my right are greater than or equal to me. So it's as if this green index is now n. It's not a valid index, but it's crossed the legal limit of the array. So n minus I could be one way to put it, or I could pick n minus 1 here and ask what's the size of this subarray from I to n minus 1. So that's n minus 1 minus I plus 1. That's the number of elements in this subarray. So that's also n minus I, this value.
Okay, I see. So you're adding, I got mixed up because I thought you're adding the index of the leftmost versus rightmost, but you're actually adding the left distance and the right distance. Okay.
Yeah.
Okay.
Yeah, we could have used the indices and work with them as well. I'm just trying to use the same vocabulary that we used last week. And so rather than store the indices of the previous smaller value and the next smaller value, I'm just computing the spans and using the spans to find the width of the rectangle. Safiq, did you have another question? Because your hand is up.
Yeah. How we are handling the case of, so suppose somewhere we reach height is 0, right? So in that case, our stack would go completely empty, right? While pre-calculation.
Yes.
And
So our stack would go
we will
empty.
mark,
Yes.
yeah, we'll mark the next index with left span I equal to I plus 1, right? We'll start considering from the just next to the 0.
So no, because we will see a value of 0. We will see a value of 0 in the array. So we will actually insert that value. I mean, our element is going to lie on top of the 0. So the stack won't be empty there. It will be this value will be the index of the place where the height was 0.
Okay. Can we have some example to explain this?
So if let's say this is 1, there's no building here. Sorry, this is index 0, 1, 2. Let's say this has a height of 1, this has a height of 2, and there is nothing here. So when we are computing the left span, our stack will initially start out with the building at index 0 on it. Right? So if I color this red, my stack is initially, monotonic stack is initially going to have this. Then when I look at the building with height of 0, I guess, I will look at the top of the stack and check if that is my that is my previous smaller value. Right? I'm computing the left spans here. So for each element, we are trying to find, for each building, we are trying to find the previous smaller building. So the previous smaller building for building 0 does not exist. The previous smaller building for building 1 also does not exist because the red building is actually larger than it. So we will end up deleting it from the stack. And so the span of building 0 is 1, the span of building 1, the left span of building 1 is also 1. Sorry, yeah, 1, because it includes the index of that building itself. For building 2, when we look at the top of the stack, there is nothing there, it's empty. So we will just end up, sorry, actually we do have an empty building on the top of the stack. Right, because when we look at index 1, we would have inserted that empty building into the top of the stack. So when we look at index 2, we will see that empty building on the top of the stack. And so that would be our previous smaller value. And so the span of building 2 would be 1 again. And then we would end up inserting, so if I color this building as green, we will end up inserting this building on top of the empty building in the stack. Right, this is the bottom of the stack. This is the top of the stack. So the span of each of the 3 buildings would be 1.
Okay, all of these 0 and 1 and 2.
Yeah, because the previous smaller value for building 0 wouldn't exist. So we would have 0 plus 1 as the left span, right? According to the code, the left span value at index 0 would be 0 plus 1, which would be 1. That's always going to be the case for the leftmost index. For this index, the previous smaller value does not exist because it would have removed, we would have removed this building from the top of the stack. And then we would have
Actually at one I was thinking it should be 2. The reason is when we are processing when current I is
for 1 it will be 2. You're right. Yeah. For 1 it will be, we will again get into this loop because the stack would be empty. The stack would be empty at this point when we are looking at index 1. And so we would set the left span of that building with height 0 to be 1 plus 1, which is 2.
Yeah, and next one. Because at that point, everything will be emptied, right? Because the stack is going to be empty because that will be the lowest most.
Yeah, the stack will be empty, but we will end up inserting the empty building here into the stack. Yeah, the stack is empty at this point. So we execute this, but then we are going to insert that building of height 0 into the stack. So when we move to the next index, index 2, the previous smaller building is going to be the building with height 0 at the, which is going to be lying at the top of the stack.
So it means once we encounter the 0, stack is never going to be empty, right?
Yes, it will never be empty. So the left span of any building after it will not go to the left of this empty building. It'll always terminate here. The left span of any building here will always terminate here.
Or maybe there is equality condition that may kick it out as well. Because if next we encounter the next 0, so in that case we have to consider the left span or right span, that new 0 index onward. Can you go to the next code one where we are calculating the span?
The right span or the
span? Yeah, any one of them.
Okay, we were looking at left span.
Yeah, the top will get the 0 because we have pushed the 0 value, and height I is currently the height I is also 0, right? So maybe equality will hold. Again, the new 0 will be kicked out, and will again store the new 0.
Yeah, but you know,
but
the
left
change. Span and the right span for buildings that have a 0 height, it's kind of irrelevant because the height is 0 for them. So
Yes.
the area of the max rectangle will always be 0. Doesn't matter what the left or right spans are.
Mhm. Actually, the way I was trying to understand is, so wherever we encounter anything the lowest most, so we are
Hmm.
going to start that point onward. I mean, that's why
Yes.
yeah, we
Yes.
are pushing the left span I plus one, and we are taking that height because that height is not going to kicked out unless we encounter the lesser than that, right?
Yeah. So
Lesser or
once there
equal
is a
than that.
building with height 0, we're going to be always using this formula because the stack will never be empty.
Mhm. Correct.
Yeah.
Okay, all right. Thank you.
Okay. Yeah, maybe you can lower your hand so that I know that your question's answered. Okay. So that completes our discussion of this problem. Maximal rectangle under Skyline. So this was the basic idea there. For every element in the array, irrespective of whether we are doing a left or right scan, we are determining the maximal rectangle which touches the roof of that building, right? And since this is, if this could be computed in constant time per element, which we could by just looking up the left and right span values, the overall time would be ordered in. So it's important to do this problem in linear time.